Hello, this is Energy Physics again for another limited lecture series in Photon. Yeah, I like that term, Photon. Photon quantum, mass quantum physics. This will be a short lecture covering just the collision, emission, absorption theory, CIE theory that I've been developing since about 2012. And it's an alternative theory for looking at what a photon is and what a mass is, how gravity and interacts with photons, and how photons interact with masses. This is primarily a short lecture in order to simplify into a nice 10-minute or 15-minute discussion the basics of the theory that we're trying to convey. This is a particle-only approach. We've completely thrown out waves as a necessity, and to avoid the confusion typically caused by modern quantum field theory and the current equations of the Standard Model, which rely heavily on wave superpositions and entanglement concepts and wormhole concepts, and we're basically prohibiting infinities and prohibiting singularities and zeros because real physics, our assumption is, must be finite. And because it's finite, it has to be quantized, and it has to have small values and maximum values, and it can't have infinities, zeros, wormholes, time travel, all that other quantum entanglement stuff that indicates simultaneity, as if mankind has the ability to look at all space at the same time, which is just not true. All of our evidence is special relativity controls the particle streams that come to us from all sources, so humans always measure everything from a relative perspective and never capable of measuring things simultaneously. So that's a fundamental basis for this theorem, is everything's finite and simple down at the Planck scale. So we'll get into this lecture with a real short series of slideshows. Start from the beginning. We first have to define this version of what is a photon. And modern Standard Model is a very, very poor job of defining what the photon is. It's very difficult for anyone searching through the mass of complex mathematics to get anything resembling a good discussion, a detailed discussion of just the photon. It always goes quickly into weak and strong force theory, and those are energy Lagrangians as well, but they never really sort out and study just the photon. It's almost as if physicists ignore it. In fact, I've met many physicists who don't understand that it's the photon, not the electron, that is primarily acting when you have a wire or a device. The photon's what's going down that wire. And I've met many physicists that focus on the electron and the particle, proton and neutrinos and neutrons, but they almost never discuss what the photon is. It's a very large weakness in the literature and in the common language of physicists to describe and explain what a photon actually is. And even worse, they can't explain the basic unit of mass either. The fermion and the quark is as far down as they've been able to go, and this theory projects a particle called a mass quantum, the smallest possible particle in the known universe, and that mass quantum forms the basis of gravity. It has a free state and a bound state, and it behaves just like the photon quantum, which also has a free state and a bound state, and together the four particles form all of the basic particles, is the stable particles of the Standard Model in a composite structure. So we're going to quickly go through that. So we first define this photon quantum and give it some properties that are very similar to a physics that is finite and doesn't rely on waves. So first we have to define what space was, and then anti-space is the formation of the particle at a certain radius, and that radius is fixed in the theory. We don't know what that radius is, but it's estimated for the mass quantum to be somewhere around 10 to the minus 75 meters, which is incredibly small. And for the photon quantum, we don't have a radius on that yet, but it may be equally small, slightly larger, 10 to the minus 40 or something. Certainly it's bigger than, much smaller than the proton, I'm sorry, and the neutron radius is, which is somewhere around 10 to the minus 19 meters in estimated size. And we're going to fix this concept called gauge symmetry, which in all the mathematics of Hermitian operators and Hermitian matrices that are done with a concept called group theory, unitary, special matrices, and group theory. The big driver is no matter what direction you move the particles or transform the particles through space, you have to follow what is known as this gauge symmetry. So the matrices are designed to enforce that gauge symmetry by always declaring that they must be unitary, they must be Hermitian, and basically identity matrices that always form complements of each other's, transform into the same thing. And that's simply just a property that says no matter where you go, no matter what direction the particle travels, its basic properties, scalar properties of mass and spin and all that other stuff don't change. And that's just a restriction on the mathematics. So we're going to do the same restriction, just from the very definition. These particles are always fixed in finite size. They always go through vacuum space at the speed of light, c. They always have some angular spin velocity, which is a constant, and it's quantized and only has one value for each energy level, no matter where you go in space or what you do, except during interactions and interaction events. And that energy level is determined by Planck's formula for photons, and we extend it to mass quantum, where the sum of the energies is equal to h dot, which is Planck's constant, h dot times nu, which is the frequency of rotation, and we're changing that view to be an angular spin velocity instead of a wave and a wavelength and a wave frequency. We're getting rid of those wave concepts. Come up with the identical same numbers, only we only use frequency, which is the spin speed, angular spin velocity of this particle around its own axis. And it's polarized in one direction and polarized in the other, left or right, spinning in the direction it's traveling and spinning opposite to the direction it's traveling, which matches the same restrictions on the photon in the unitary U1 matrices. So there's nothing different between this theory and quantum field theory in terms of fixing these properties as gauge theory. We're just restricting them from the very definition of what the particle is instead of having to prove it with matrix math. It doesn't predict anything. Matrix math doesn't really predict anything until you manipulate it with the other particles. So there's very little to predict and get out of the unitary representation of photon, which is why most physicists just don't represent it. They don't talk about it. It's very, it's trivial from their perspective. But I think this is a much more accurate representation of what really happens down at the Planck scale for real physics. I don't think there's a superposition of waveforms that then can collapse into a finite measurement. I think that's all mathematical fantasy, if you will, that's useful to give a good approximation of what's there, and it's the best we've been able to come up with is the current quantum field theory of the Standard Model. But I believe this is a much better representation of actual physics, finite physics at the Planck scale. The particle has a finite size, it goes at a finite speed, it has a finite quantized angular spin velocity, and you can measure that as an energy level by using Planck's equation. The sum of the energies is equal to h dot nu. We add the gravity component in there, plus or minus g dot, which is the gravitational equivalent of Planck constant, and that's the g dot times omega, which is the mass quantum angular spin velocity, also fixed and quantized to have only one value for every energy. So the summation of those two forms the basis of all interactions between photon quantum and mass quantum that are interacting to form gravity. mass quantum interact with other mass quantum to cause gravity. Photons interact with other mass quantum to cause photon inertia, acceleration, and momentum. So it's a very simple but potentially highly accurate model of how the universe works at the nuclear scale, at Planck scale and below. We've estimated that the mass quantum has a particle mass somewhere around 10 to the minus 51 kilograms, and a particle size, radius, somewhere 10 to the minus 70 or 71 meters. So this is very, very small, much smaller than anything that theorists have been able to come up with in their current derivations. If they've been able to estimate size at all, it's just been a Planck scale estimation, 10 to the minus 31 or 32. So we use this basic equation that you see there. Sum of the energy is equal to the sum of h bar omega plus the sum of g dot omega. We replace the photon omega with nu, the symbol, Greek symbol nu, if we wish. For monochromatic energies, the calculation basically is divided into buckets, the same kind of energy buckets that you measure in a particle accelerator. You know, certain photons have certain energy levels and certain fermions have certain energy levels, and there's thousands of them, and you group them together and you calculate and sum up all the mathematics and sum up all the energy values and you get an end result. And that's how you calibrate your particle accelerator, and you put these different energy levels into buckets and you add them all up. That's exactly what this theory does. That's why the people I've showed this theory to at the Snow Lab conferences that I've been to, mostly experimental physicists, they really think I'm on the right track with this, and they're really not getting much help from quantum field theories other than to point in the right direction. It doesn't help them measure anything, and they have to discover everything as an actual particle anyway. All the theoretical particles are not really helping them that much. There's very little guiding them in terms of look in this specific area, other than the last help was the Higgs particle. They were able to look in certain energy brackets and eventually discovered what they're calling the Higgs, which is just another big chunk off of a proton that's been smashed apart. And it's a composite particle also made out of these photon quantum and mass quantum in both free states and bound states. The bound states form the finite structures of the standard model. So h dot is 1.05457180 times 10 to the minus 34 meters squared kilograms per second. That's a joule second also. G dot, the gravity version of that, is approximately 1.05509.405 times 10 to the minus 77 joule seconds. Same value of energies when you multiply by the angular spin velocity. They're a constant. And we're going to define again the standard model version of this so you kind of understand how this ties in. The CAE theory is kind of a replacement for the difficulty of mathematical calculations required by trying to get any kind of numbers out of the field theory. These are all energy Lagrangians, but they basically start with the concepts of the photoelectric effect and how those are put into a standard matrix mechanics by Heisenberg. And the Heisenberg uncertainty principle drives, you know, the accuracy of the momentum versus the distance, or the accuracy of the energy versus the time. And we're saying, you know, the real particles, they don't care about that, you know. What's interesting is that when a photon quantum or mass quantum is always traveling at the speed of light, it knows what its momentum is. It's constant. It's whatever mass it has times the velocity constant of c. So there's no need to have any, you know, uncertainty in what the momentum is of a free state photon particle. And so the accuracy then of time becomes very accurate and precise for both of those. So there's no need to have Heisenberg in a free state photon quantum. The same is true for free state math quantum. It knows exactly its absolute space. Only the particle knows that, its speed in relative to absolute space. And we're pretty sure that it's somewhere around the speed of light, maybe it's slightly more, or slightly less, and over time it may have changed as it traveled through the universe and reaches our local space at cosmic background radiation energy levels of 50 hertz or 10 hertz or 5 hertz or 2 hertz, almost absolute zero. It's very, very cold, even colder than cosmic microwave background energy of a photon arriving in local space that's been traveling for 13.7 billion years, and that's at 2.7 Kelvin or so. That's cold, and those energy frequencies are up in the millions or so of hertz. So when you do the transformation on temperature to frequency. So the quantum field theory, due to matrix mechanics, creates this special particle because of gauge symmetry requirement that, basic scalar properties and the identity always summing up to be a probability of 1 has to be held as a probability of 1 through all space transformations. So the matrices that do that are manipulations of what are called unitary matrices of value 1, unitary matrix of degree 1. And it's such that A times its complement is a non-zero multiple of the identity matrix, or usually it's the metric tensor, typically, which is an identity matrix with all the ones going down diagonals. And it's a product of the unitary group with a group of all the other positive multiples of identity matrices. The special unitary is also used to calculate the other particles of the standard model, the electron, the neutron, proton, and that's usually in a special unitary 2 matrix, which combines with with the unitary 1 matrix. You do a cross product multiplication in order to get the values of energy, Lagrangian energies, out the other end, and that becomes the electromagnetic force interaction, and that's typically where most calculations, representation of what these matrices look like starts. Though it's always got a special unitary 2 times a matrix cross product of unitary 1, and that's explaining your electromagnetic force interaction. There's almost never a representation of just what is a photon in free space. It's a U1 matrix. And so the ones are usually on the diagonals rather than the cross diagonals. Just represent how you represent it. The key aspect for this gauge symmetry, the matrix is symmetric, and it has an abelian matrix which has a zero commutator, which means that AB minus BA is equal to 0. And if that's violated, you basically have some special conditions on that, which are conservation of energy type concepts. It's called a commutator, and if it's 1, it's got other properties. It's typically also a Hermitian matrix where the matrix transpose, represented by that cross, instead of being a small t, physicists for some reason want that cross in there. And, or an exclamation point, depends on how they represent it, standard matrix math. But it's equal to Hermitian matrix whenever that transpose is equal to m times the transpose of the matrix and its conjugates. So you learn how to do a transpose. You basically put all the columns into rows and rows into columns. That's a transpose of the matrix, and then its conjugate is a complex conjugate where all the pluses become minuses, including the complex numbers. Becomes 1 plus imaginary becomes 1 minus imaginary. So that's how you get a complex conjugate transform. And whenever those two matrices are equal, that's called a Hermitian matrix. And most of the calculations in quantum field theory are Hermitian operators, Hermitian matrices. They're operators because you basically cross-multiply an operator with these unitary or special unitary matrices in order to get your values that you're looking for, get the matrix to collapse and the identities to drop stuff out as zeros, and it comes out to a single value. Otherwise, it's a waveform when you basically transform the matrix into, say, Schrodinger equation or something like that. So the standard model describes photon as a tensor field unitary U1 matrix, and it's a Lagrangian energy with global symmetry where the waveform is equal to G, the metric tensor, times the two forms of the waveform. And G is a very common identity matrix used to raise and lower ladder indices that are typically at the bottom of the matrix or the upper part of the matrix. And that's a method of changing its changing its form to do other types of calculations. If A transpose A is pure gauge, it changes nothing. That's what you're doing with gauge symmetry. If it's dynamical in a U1 times SU2 cross multiplication, then you've got other properties describing what they're called a fermion, electron, lepton, bound state concept of electromagnetism between photon and some other mass. In this case, that mass is a bound state mass quantum. It's also interesting that the U1 is, again, this circular nodal concept that if you calculate, these various poles and zeros, you'll end up with these points around a circle. Typically, it's represented by an exponent of to the minus I phi times again that's a wave function position of x and t. So it's a probability is conserved, which is what you need to have. It's why it's gauge symmetric when those two conditions are preserved. One's a complex conjugate of the other, which is the same thing we stated before. The special unitary matrix, again, is no different than a unitary other than its determinant is always 1. You know how to calculate matrix determinants when you were in high school. But these big matrices require a computer. It's just kind of tough. And there's two conditions on that. It has to be invariant under gauge. Phase transformation of the fermion wave functions. Fermions, again, are all the particles with mass. As we described before, have to hold. And then gauge transformation of vector potential, which is, again, a representation of matrix form, preserves the probability to remain 1. And that's really all it's doing. So the CAE theory does that all already. Everything's fixed, everything's finite, nothing changes. It's one energy level, one angular spin velocity with a specific energy value. It can only go at the speed of light, and it only has two polarities, all in the direction of travel or opposite direction of travel. So all that's already fixed in the definition of Planck scale CAE. You don't have to have these matrices to prove that or restrict that. And that's one of the reasons that form of the theory is, so much more powerful, I think, to describe real particles than to have these mathematical representations that mislead us in how we identify the world as always a wave when in reality everything's particles. And I think that's hurt us rather than helped us. And again, your mass quantum versions and definition, the masses are all represented typically by SU2, special unitary matrix 2 form. And again, the restriction for that is that those matrices always have determinants equal to 1. And they're members of the larger Lie group algebra, which again are all skew, n by n skew Hermitian matrices in the Lie brackets. Lie bracket is again a bracket term, and it's given by the commutator AB minus BA is equal to 0 or not 0. That's a test for gauge symmetry. Now, we've got this Feynman diagram that has been very powerfully used to represent how these particles interact in real particle accelerators. Sometimes I wish they'd show the actual pictures, because this is a close representation of the actual picture of the particle travel through the detector. Notice there's no real waves there. They're representing this photon as a wave, but it's really not. It's a particle going at the speed of light with an angular spin velocity, and it could be represented that way instead of as a wave. It doesn't have to be represented like a wave all the time, and that's part of the problem. So it goes from a positron, electron changes from a positron, electron changes from an electron to a positron by losing one of its photons at whatever energy spectrum it gets emitted at, and that's just traveling at the speed of light till its next event, and it could hit another electron, which would be electromagnetic energy, or it could hit another proton or fermion, which in this case is a quark interaction. And that quark is made up of these bound state mass quantums, so it could be actually interacting not with just one quark, but down inside there's always this special absorption emission process that couples the photon quantum and couples the bound state mass quantum to where it gets absorbed, and then sometime later when another piece of energy comes in the form of a photon or the form of a mass quantum, it can eject that out, always again at a escape velocity which equals the value of c, traveling as a constant through space. So you see there that gluon gets emitted. Well, that's again, a gluon is a heavier form of a photon. Why? Because it's in a bound state with some tiny piece, composite piece of the mass quantum. So the quark is actually a composite particle of bound state photon quantums and bound state mass quantums, and free state mass quantum can come in and hit them, and free state mass quantum can hit them, and free state photon quantum can hit them, and that one causes the inertia of photon inertia, the other causes the inertia of gravity. So even in this Feynman diagram, we have this human concept of time, but it's really just a single event. You know, the particles don't care and track time. Humans track time. And when we track time, we have a special relativity delay that happens from the time in the past where the electron exchanged in its event and became a positron by losing its photon, and it travels for an unspecified amount of time and space by special relativity, always at the speed of light, takes a time delay. If it encounters anything, it travels a longer distance to get to us because it's got to go zigzagging and scattering back and forth at different scattering angles between the various particles that it hits and absorbs and emits from. And those could be other electrons changing a positron back to an electron, emitting a neutrino, or a quark that emits a gluon that we can't really measure, coming from a quark to an antiquark pair, or a Higgs boson that is consisted of W pluses, quark antiquarks, top quarks, down quarks, bottom quarks. You know, the Higgs has got a huge number of particles that are inside of it. And of course, we represent that Higgs interaction again with the U1, SU2, special unitary, and then special unitary 3, which represents the other fermions in the nuclear structure. So you combine all three together, you've got the full Lagrangian structure. Those are all energy Lagrangians in the calculus that includes the Higgs component, the Yukawa component, and these basic three matrices are the calculating mathematics. And of course, we don't have to use this if we understand that these particles interact in a small event, and they're just interaction of absorption and emissions or collisions at the Planck scale, always changing their momentum, changing the inertia of the particles as they interact. So this collision theory, the CAE theory, is just as valid at the Planck scale and comes up with the exact same energy numbers as cranking through these very complex calculations of the quantum field theory special matrices to arrive at some supersummed energy level anyway that the particle physicists add up in their detectors, detecting energy levels, and computers summon all that up to have a peak or a spike where you can claim, yes, that indeed is a particular type of particle. You don't know it's a spike till you sum up all the energies and say, well, there's 50,000 particles of tiny little peaks of energy all adding up, and that's what this Planck scale theory does. You find the peaks by summing all the Lagrangian energy scales using the Planck's equation that we've developed and the concept of angular spin velocity instead of waves. This is a chart of all the masses. We do believe the photon has a very, very tiny amount of mass, somewhere around 10 to the minus 40 to 10 to the minus 60. It's just too small to measure. Physicists, they love these zeros, but real life is finite. There are no zeros, there are no infinities, so we need to find out what that value is someday, if our detectors are ever good enough. And notice the electron and positron are 9.1 area, 10 to the minus 31 kilograms. Proton minus 27, so it's lighter than positron. It's heavier than positron by order factor 3. Neutron is slightly heavier than the proton, obviously. And then we get the mesons that have their own, which are composed of quarks, top quark, bottom quark, whatever the total spectrum is of the Gelman quark matrices, and there's eight of them right now. And you get the leptons, the mu electron, the standard electron, the standard positron, its antiparticle pair, and then the mu electron, tau electrons. They all have masses now. 3 types of masses. That was discovered by Snow Lab, and the Nobel Prize was given. The fact there's 3 of them. And the interesting thing is, quantum field theory doesn't predict that. It fails to show that there are 3 possible masses to the neutrinos. So that's another problem that this CA theory says, hey, there's no problem with that. It's just more standard model composite mass quantum in bound states coming and interacting from free states, and they get absorbed, and they stay there until enough energy can release them. So this theory has no problem predicting that there's 3 masses, additional mass involved, and it can handle the Higgs mechanism just as easily. Higgs is a composite particle of these photon quantum and mass quantum, and we just calculate the number of them. And the theory will allow you to do that. Here's how many photon quantum and here's how many mass quantum are bound up in the Higgs particle. It's just a super summation of the energy levels of the Planck constants and the gravitational constants of these 2 particles, super summing and totaling until you get the same energies that you measure in the particle accelerator for a Higgs particle energy. Notice we've assigned a value to that mass quantum as our best estimate based on calculating some masses and densities of neutron stars and Planck stars and supernova to get an estimate of what kind of mass could get through them and how long it would take. So 7.37261954 times 10 to the minus 51 is as accurate as we could make that measurement. And again, it's all new theory, so that number could be off by quite a bit. And someday people will discover a number for that, I'm pretty sure. And LIGO, the experiment with the 2 neutron stars, is the first evidence of the existence of this mass quantum. So it's not a gravity wave. It's a pulse stream of very, very tiny, very, very small mass quantum that are disturbing the electrons and the protons in that steel beam and making the interferometer mirrors vibrate. So change the way you look at that experiment, and you begin to see the first evidence of mass quantum. It's staccato. It's a stream of particles. It's not a wave. When you look at the energy values and the detector values, they're all over the place. They're not smooth waveforms. People try to make them smooth waveforms, but they're just classical particle streams to look at. So real quickly, we'll end this lecture with going with what is the smallest possible finite quantized particles. We're postulating that as the mass quantum, very tiny, and it moves photon quantum around in curvatures, and that's because of this phenomenon known as screening, where you got the halo of mass quantum that form dark energy and dark matter phenomena out of the universe is almost a homogeneous a halo of particles all around us, and there's a number of them hitting the photon in any given second in time. And the problem is that it's a screening phenomenon when the same mass quantum from all directions go through the Earth, which absorbs some of them. So the end resultant is a displacement in the direction of the Earth caused by the differential in the number of photon and mass quantum that are interacting, with more of them causing inertia and motion in the direction of the planet because there's more of them impacting and being absorbed and emitted from the outer sphere than underneath my chair, where gravity forces me down because there's not enough mass quantum to push me back out and make me float in space. Whereas in space, those collisions are all balanced for the most part, still zigzagging and vibrating in space, but still pretty much being equivalent from all directions, and so you float, and that's gravity. And photon quantum can do the same thing. They do it in the Kashmir effect. They do it in Cherenkov radiation, which we've explained in the other slides. I don't want to get into that, but that's how you tell the difference between photon quantum and mass quantum. Is one's being radiating photons as they approach the speed of light, and in a gravity well, photons don't get radiated. It's mass quantum that get radiated, and we can't see them. And with the Casimir plate, there's just not enough source material, mass quantum or photon quantum coming from the inside of the plates as there is from the outside, impacting from that mass halo, and it moves the plates together. It doesn't require a vacuum energies where something is created out of nothing, as the current quantum field theory tries to postulate. This theory we're at is at the smallest possible scale, and it has to map in with same numbers and super summation of all the energy levels. Has to scale up to the same measurements in the Newtonian scales without changing this concept of 1 over r squared. It has to map into that, and those equations and numbers have to be the same. As is the numbers that come out of the quantum field theory, this theory has to map into the same numbers, and it does. So it doesn't change or remove any of the current theories. It just allows more precision in calculation and a better understanding of how nature actually works. And the thing with general relativity is it operates actually at the Newtonian scale for the most part, and it smooths all this stuff out. So the general relativity is completely unable to handle Planck scale perturbations and Planck scale zigzags and Planck scale particle analysis. It can only handle stuff at the large size scales of planets and neutron stars and Planck stars and galaxies. And again, it's just an approximation. Same here. You've got the collision theory, CAE, on one side that's more precise measurement. It's got a certain compression radius that at some point it reaches a maximum and then explodes. And we've got to define that. It operates below the Planck scale of 10 to the minus 33 centimeters and below the Planck densities of 10 to the minus 93 grams per cubic centimeter. And in the middle, you've got particle theory, which is last of the Standard Model, which is the last discovery was the Higgs boson at a quantum scale and size of 10 to the minus 13 centimeters. And again, our mass quantum particles down around 10 to the minus 71 centimeters, so meters. So you see the challenges for our detectors to actually detect those and supersum them to equate the gravities expected in dark energy and dark matter. So the mass quantum is dark matter. It is that missing particle out there that's causing everything to mysteriously collapse into gravities and black holes and Planck stars. And at the universe scale of 14.375 billion years, it's been traveling that long, and it's really cold by the time it gets here if it's never interacted with anything. And it can't fuse like photon quantum can, so it doesn't change its energy level. So we can define mass in the Standard Model as fermions. These are all separated from bosons by the calculation of this SU1 matrix having integer momentums and spin states. So that's how fermions are isolated and separated from bosons. Bosons all have spin 1, whereas fermions have half, 3 halves, 5 halves, 7 halves, etc. So again, that's just a matrix calculus on Hilbert space state vectors with probabilities of 1 that describe molecular orbital shells that we already described 1s, 2p, 3p, g's, and f's. And they're all given spin momentums and quantum state numbers, basically, that are half integer in the case of fermions and single integers in the case of photons, and integer 2 in the case of, I think, W plus, W minus, gluons or whatever, and weak particles. And the Higgs has 0 spin, which makes it even more fascinating. And you have to keep up with that calculus. The other calculus we need to be aware is that neutrinos violate symmetry. It's the first particles that do. They have what is known as chirility, helicity for relativistic waveforms, and that means that basically they only have left-handed spinning neutrinos. There are no right-hand spinning neutrinos, so the symmetry is broken. And that was, part of the weak force calculation in order to describe how, standard nuclear radiation emits an electron, changes to positron, and gives you a neutrino back out of that, but only left-handed spinning neutrinos. And the last thing we'll discuss is that we do need to always be aware of special relativity, but there's no trains, there's no planes, there's no spaceships, starships traveling at the speed of light, no elevators that travel at the speed of light. So for God's sake, physicists, stop teaching that junk to students, okay? Teach them how special relativity works at the Planck scale on electrons, photons, and mass quantum. And it's basically, we're always looking in the past as humans. Only the particles themselves know absolute space. Everything that we measure is relative space because we're human and we're big and we're large, and we always rely on an event and an emission coming to us into our detector from the past, and we can only measure one value in the present. So that value is the value we measure in the detector, and it takes a finite amount of time. And instead of changing frequency or wavelength, all that's happening is for every interaction event that the photon quantum or the mass quantum counters on the way from its original emission point to its final detection in the detector, the only thing that happens is it's traveling a longer distance, not slowing down. It always travels at the speed of light, but it has to travel a longer distance because there's more scattering angles as it hits these different electrons or protons that are in the crystal lattice shells of molecules. And that's an index of refraction. That's all that is. The photon travels a longer distance, and when we as humans look down on that, it goes, well, why did this photon take longer time? It must have shifted its wavelength and all that other bullshit, and we call that an index of refraction. But all that is special relativity going from one material, atmosphere to glass or whatever, delaying the appearance of time, but it's simply causing the photon to travel longer distances and be absorbed and emitted for every particle event that it interacts with inside the molecules which contain the electrons and protons that the photon quantum and mass quantum interact with. The mass quantum does the exact same thing. We just haven't yet discovered special relativity for gravity and mass quantum, but that's what it is. Here's another representation of that, where you've got an electron shell, electron energy value, and then you've got some proton inertia, and of course the proton is traveling down a pipe or accelerator pipe, and the electron emits a photon and then gets absorbed by the proton and then gets emitted again, and it accelerates in its inertia as it travels down to another mass quantum event, and that all takes time. And the energy of that measured is energy equal to h bar omega, and if we wanted to add gravity, it'd be plus or minus g dot omega as well. And these different energy levels are then detected as quantized energy levels in the various detectors based on how fast the angular spin velocity is spinning at a single value for a single energy as a quantized state. And this is their attempt to measure the curvature of general relativity with the same concept. I'm not going to try to explain that later because we have that in a gravity lecture. So we try to bend and bucket these into mathematics that describes the difference of discontinuous states that Niels Bohr and Heisenberg argued over what are these instantaneous jumps, and that led to their entire reason for using these matrix maths to begin with and restricting it to the Heisenberg uncertainty principle. The particles don't deal with that. They just accelerate and decelerate in absorption and emission curves, always at the same escape velocity c, and that's because the mechanism of absorption and the mechanism of emission is identical. The photon and the mass quantum interact exactly the same way, and when new energy sources come in, they get ejected at exactly the same velocities every time. That coupling is not and the electron difference between the proton, it's something inside the electron and something inside the proton are identical in terms of their coupling. And it's very likely the way that mass quantum interact with photon quantum, and they're always the same until they emit, absorb, and release their energies. And this is just a representation of the scattering angles that are possible, the different statistical phenomena where these energy levels can be higher or lower based on the energy that comes in, and the scattering angles will change. And that's what forms the light and dark patterns of real photon, real particle, real mass quantum hitting detectors, and that's not a wave. That's just a bunch of particles that are supersummed over time that form a composite image, and that composite image has light and dark spectral lines. And that's where the dark lines are where there's no particles that hit, and the light lines are where the particles hit, and they scatter through different scattering angles to cause that phenomenon. And it has nothing to do with waves. That's not a waveform. It's simply a composite illusion over time of scattered particles that happen to hit in a pattern. And that's the way we need to look at it. It has an angular spin velocity and frequency in terms of what those energies are, and they're distributed across the spectrum, but quantized. There's certain values that they're not permitted to have based on the energies of release and energies of absorption into the proton or the electron that they emit or absorb. These are the mass quantum and photon quantum trying to stay in orbit with the doublet pairs. I believe quarks are pretty much formed out of these things. Composites of these things is what constitutes the quarks. And those all sum up into the other fermions of the mass particles of the Standard Model. They start with quarks, and then the quarks build up in triplet pairs from this basic. And there could be several hundred million of these things that form a quark because the particles are so small. They clump together in free state and bound states, and they form these energy spectrum. Again, the spin frequency being constant, and that's why it takes a finite mathematics and finite superposition, supersummation of all the energy Lagrangians being added up, and it looks like this energy distribution pulses, not continuous mathematics at all. We've got to get away from continuous mathematics. And here's this screening phenomenon again that forces this Casimir plate, for example, or the Earth, causing gravity, screening the stuff that's got the mass fermion clumps together, absorb and emit the mass free state mass quantums as they go through, and because there's a smaller number of them on the inside than the outside, these things eventually drift together because their momentums and their vector velocities are altered toward the center of these clumps. And this is just the process of screening that causes gravity, and it's dark energy gravity, and the dark matter does the exact opposite because there's nothing on the outside to hold these things, bind these things from spreading out from the inside. The mass quantum are just continue to expand at dark energy speeds because they are the dark energy phenomenon, and there's nothing to hold them back, nothing to decelerate them because there are no mass quantum particles out in the halo outside of their existing boundary of expansion. But there's still enough of them on the inside of their expansion for the last 13 billion years to continue to impact everything and cause gravity at its current levels. Gravity could have been much, much higher in the past. And eventually forms these gigantic galaxies with Planck stars in the middle of every one of them and in giant threads all through the universe, which is our current view of how we actually map these with the telescopes. And hopefully the James Webb Telescope will show these clumps and show these small particles even more likely to detect how they interact both with the dark energy expansion because there's nothing to hold them back, and the dark matter collapse, which is caused by screening. And Casimir plate, for example, has the same phenomenon that forces the plates together as the molecules get impacted with a differential of numbers on outside versus inside. And that's the end of the lecture today. Hope you enjoyed it, and it's as short as I can make it right now. I'm trying to make short lectures, keep the topic isolated and focused. And I try not to mention too many extraneous things unless they just come in my mind as something interesting that you may not know or be aware of. And I just try to throw those in there so that the overall picture of what I'm trying to explain has some meaning to you. So good luck in your pursuit of studies if you're studying physics, and I really hope that these concepts will make major changes to the way we calculate real numbers and see real physics at the Planck scale as the mechanism for what's actually happening. And we start throwing out these wave functions and these wave concepts because they're just not needed and not necessary, and they cause us such confusion, just like it did with Newton and Huygens a long time ago, arguing about whether things were waves or particles. And Newton said they're particles, and Huygens said they're waves, and Einstein said they're particles because of the photoelectric effect, and then what's his name comes along and says, no, even electrons can have these patterns. And so, yeah, electrons do because they're particles, and they can make composite illusion pictures just like photon quantum do. So it's, go down the particle path, and you'll get the most accurate form of physics, and everything's finite. Reject infinities, reject zeros, reject wormholes, reject time travel, reject quantum entanglement. All that stuff is just, fantasy, no evidence. Even quantum qubits and quantum computing, there's nothing simultaneous, so we're kind of fooling ourselves with this entanglement quantum concept because we're not considering special relativity interactions down into quantum computing bits that we calculate. Photons go from one point to another and they cause a bit, and it takes time, and it takes special relativity time. So we're never going to get any faster computers than the distance that the photon quantum has to travel to create an event with one of the other fermions. And your quantum computers have fermions and mass quantum that are in bound states, and they have free state photons and bound state photons, and they're all delayed as they travel from an electron to a proton and travel to a register or a register structure that you've created using their molecules. So get real, get the science right, and you'll understand there is no quantum entanglement for the same reason. Take care, and I hope you enjoyed it.